Hello and welcome to week 4. I want to redo this stuff because again, it's a new book this semester. We're going to go into the Kangaroo book, and it's similar to the other book. It's just the structure a little different, and I just wanted to, like I said, redo a bunch of videos. So if you look, if the video has like a white background, you see how right here is dark tan gray. That means I redid it for 2025. If it's white, it means it's from 2024. Sometimes it doesn't matter, sometimes it does. So you can watch the old videos for like week 4 going on, but I left them up. It doesn't hurt to watch them, but again, I wanted to kind of refocus and make new videos. So yeah, so let's dive in. So this is basically chapter 1 of the Rue book, as I call it. Chapter 1 is kind of really foundational, so I also kind of covered chapter 2 a little bit in this. And then week 5, we'll go real lightly onto tokens. This book goes really into detail on tokens, and as long as you really understand the concept and can think around the idea of tokens and embedding and encodings and things like that, I'm happy. You don't need to know the difference between like byte-wise encoding and this. I don't care. Okay, you do need to know why encoding is important and how it can affect the way you handle data. Okay, but it's becoming less important as time goes on. So here's a picture I saw a while ago, but it's machine intelligence is the last invention that humanity will ever need to make, and this is very true because we're seeing a lot of big changes in a lot of big fields directly related to AI. AI just released deep research, and I've been using it, and it's amazing. In theory, the O3 model outperforms most PhDs at like a 98% level. So now we have tools that can help us with our knowledge work. If we think back in the past, we had tools that could help us with our manual labor. We had, maybe shovels and things like this. Then we moved up to farm equipment. We had a tractor, and we move on. But there's only so much that can be done in terms of helping us with our knowledge work. We went from like an old bad site, like an old Netscape, from 10 years ago, and bad search engines, so really nice Google search engines. Email, but we're still very limited in knowledge. AI is finally getting to the point where it can actually really help us come up with better answers, better decisions. A tractor can do more than just a single farmer can do. And it's getting to the point now where if I ask and prompt the right questions, Chat GPT and artificial intelligence can get more done than I can alone. So it is relatively important. And going on to that is why this class is focused around big data. Okay, and probably actually I got a little slide here, and it's not even the best one. When I say 10, 15 years ago, all big data was something else. A lot of it was sensor data or sales data, or some type of something else. Now, at least in my opinion, a lot of big data is all LLM related, or at least processing LLMs. We're doing things that we could never do 10 years ago, 5 years ago, because of LLMs, and not any particular model or anything else like that. Not like, hey, what's it? No. We have, these huge data sets of spoken language. Metro receives, I don't know, let's say 1,000,000 calls a month. I don't know how many they get. What if we could take all those 911 calls and see patterns per month? We'd assume that heat stroke happens in the summer and, I don't know, freezing and hypothermia happens winter. But what if we could dig in deeper? What if we could really dive in and factually prove certain things? What if we could look at, millions of customer complaints and not customer reviews for a particular type of product and really pull out what are they saying? What are the top 10 pain points? What are the top 20 pros? How can we make this better? And that's really a point where we're at with LLMs. That's why businesses use them so heavily. So anyway, so machine learning goes back to the 60s, and there's a thing called think of machine learning wasteland or desert. That's in the mid 90s. But for a lot of this class, we can say, hey, deep neural networks and neural networks kind of happened in 2012, 2010, something else like that. Then 2017, a paper was released, Attention is All You Need. It kind of made this attention model. And we'll talk about lightly. You don't need to know a lot about the attention model. Basically, what you need to know is that it allows us to understand context of a sentence. Let's just say that, or context a little bit better. And it allows us to parallelize. So those are two really big advances. Then GPT-2 was released kind of in 2019 by OpenAI. I think that was when it was. Um, you can make GPT-2 a little bit, maybe not on your home computer, but if you have a decent enough computer, you can probably redo GPT-2. I was going to work on it when I break, just never got around to it. And we go on, and it kind of goes on. This year, I mean, I just added this. We have DeepSeek R1. There's a demo on, I think, LinkedIn. I think I posted in this chat. DeepSeek R1 is really pretty amazing. It is, it's open source, which we'll talk about today. We have OpenAI O3. I don't know why I have a capital there. That's not released out to the public yet, but it will be. There's O3 Mini that's released to the public. There's Deep Research and Operator. So we're in this time where there's a lot of iteration, a lot of change, a lot of acceleration. It's important, at least in the back of your mind, that says, hey, I saw something about this. I don't have time maybe today. Let me look tomorrow and kind of interrogate it and dig in. That's what I'm hoping that you can have time to do. You know, that you say, hey, you know, what is Claude, anthropomorphic, you know, what's their model like compared to ChatGPT? It will do nothing but help you, you know, trust me. So it is a really nice time to be in AI. It's really chaotic. There's a lot of changes, but it is a nice time. So let's dig in really what AI is. And some of these slides I use when I do presentations. So you'll see the word clinician, things like that. But it's hard because we have the word artificial or artificial intelligence. And truly, artificial intelligence is not really that intelligence, as I tell people. And we'll kind of look back to the book here after a couple of slides. But AI could be like linear regression. So when we say artificial intelligence, we're not always talking about the most intelligent model. It's a very, very broad scoping term. Okay. And like I said, the way I think about it, it's just kind of linear regression. You know, if I sell, you know, 2 items this month and 3 items next month and 4 items the month after that, I could say maybe I'll sell 6 and 7 the next 2 months. You know, it's, you know, linear regression, certain things that are kind of just low level, that can be considered artificial intelligence. It's this very broad, big scoping term. So it doesn't have to be intelligence as you and I think about it, okay? It doesn't have to do anything really cool. Now, machine learning, so for me, machine learning is you take that to the next step. You know, if you can predict X, Y, and Z based on other things. So maybe not necessarily linear relations, okay? Things that might not be super clear. You're finding patterns, and that's more deep learning, but you're predicting things from a bunch of other things that may not be directly related. Yeah. So, you know, we know that people that go through college generally have a higher income, but they also live longer. Maybe they also live happier. Maybe they have certain type of cars. Now, these type of non-traditional, non-linear predictions can be thought of as machine learning. Okay. Now, in the red here, we go to the neural networks. This is where a lot of the interest is. This is where it's fun. It mirrors a human brain. And this is where I get involved. So Richard is me. I'm a neuroscientist. I study the brain. I study neurons. I study, you know, I'm a computational neuroscientist. So I'm not a business person. I mean, I work full time at United Health Group, a Fortune 5 company. I work at Optum. I do machine learning. But what does machine learning and neuroscience have together? How do you pair that two together? And it's a fair question. And the answer is that everything in red, we've designed after human brains. And I'm an expert in the human brain. And I'm also a computer nerd. So that's how it pairs together. Deep learning, we generate these neural networks and then we train them. And once we train them, we kind of expect them or hope that they do what they were trained to do, similar to humans. We learn how to do things, walk, talk, speak, not walk into a wall. And we learn this training over time. So that's basically what deep learning is. Deep learning is the idea that we can use a neural network to kind of detect patterns. So we're kind of breaking a picture apart, and we're saying, hey, what patterns do we have? You know, what does a car have? Well, you know, if I look at it outside, it's 2 circles. Almost every car in America has 2 circles on the side. You know, like a motorcycle has 2 circles. So how do I know the difference? Well, a motorcycle doesn't have a roof. A car has a roof. You know, I mean, you start finding these patterns. We do it automatically, but we have to train machines to do it. Now, the next thing is generative AI. So what is generative AI? Sorry, one second, I just saw something on the screen. Generative AI is moving away from pattern detection, where we're trying to, and it's still prediction, but we're trying to generate something. We're trying to not just predict, we're trying to generate. So we're trying to make fake hospital data. We're trying to take it to the next level. We're trying to generate a paragraph. I'm giving you a paper and it's making a summary. This is kind of what generative AI is. So, we're taking regular data and now we're generating it somehow. We're moving it to the next level. We're doing generative AI. Next slide. Come on, machine. There we go. So here's we call it in silico neuron and a real life human neuron. Okay. And again, a lot of this I use more for providers. I don't need to get a lot of in detail here, but this is a machine learning neuron. This is how we do basic machine learning. Okay. And this is how we as humans do learning. It's a very similar process. They're weighted or they're designed from the same thing. Machine learning, if you have inputs and they don't create an activation function, they don't reach a certain threshold, nothing comes out. Same thing in our cells. Okay, if we receive inputs from the dendrites and they don't create an action potential, it doesn't forward feed. Okay, so they're very similar processes. When we talk about training a neural network, it's just similar to learning. We go over it, we update the weights. It's how we learn something. It's muscle memory in some ways. So now, how is machine learning just intrinsically different than programming? And this is something that is hard to understand. And if you go to like YouTube or TikTok, and there's those there's videos of like, hey, how do you tell somebody to open a door? How do you tell somebody to make a peanut butter and jelly sandwich? It sounds really simple. Make a peanut butter and jelly sandwich sounds very simple, but it's very, very, very complex. It'd be hard for anybody in this class to actually write down a list of instructions to make a peanut butter and jelly sandwich. I know it sounds crazy, but it's true. Because you have to be very pandactic, very, hey, unscrew the lid. Well, how? Just keep unscrewing it? Do you unscrew a lid for like 2 hours? So to open the peanut butter jar, how long do you unscrew? Maybe 10 turns? Okay, then what do you do with the lid? We put the lid on the counter. Okay. Then you pick up the knife. Okay, I got the knife. Then what do? Put it in the jar. Okay, then how do do you scoop a whole thing up? You have to be very, very, very specific. You can't just say make a peanut butter and jelly sandwich. No. Hey, fine bread. Untie the twisty thing. Actually, I got one right here. Untie the twisty thing. Remove 2 slices of bread from maybe the middle. But you have to move. It's really complex. Okay, so that's traditional programming. You have data, you have rules, and then you get output. Okay. Now, with artificial intelligence, with machine learning, we do it kind of different. You do it kind of maybe how we as humans do. You have a process, which we'll call data in here, and then you just watch the person do it over and over again. If I watch somebody make a peanut butter and jelly sandwich 10 times, 15 times, 20 times, I bet I could learn how to make a peanut butter and jelly sandwich. I bet I would watch them unscrew. 3, 4, 5, 5. They put it down. Okay. Next, this one only screws. I could learn something new from watching people. So that's this right here. Okay. So it's a paradigm shift in the way that we attack problems. In the past, like I said, with traditional programming, we came up with this, hey, here's your data, and we had these 4 if loops and these loops, and we just loop, hey, if it's not this, do this. If it's not this, do this. If it's not this, it's this. Sorry about that. Machine learning, we get a bunch of data and a bunch of examples and say, hey, this is what we want. You figure it out. And it comes up with rules. That's the training process. So this top thing is all I really want you to kind of focus on. So that's one of the big paradigm shifts. Let's keep going forward. Okay, so now, sorry, I'm just, okay, so when you talk about large language models compared to traditional NLP, one of the differences is it can understand context. And you'll hear me maybe not in this lecture, talk about how machine learning and OpenAI and Claude, these LLMs aren't very good at context. Compared to human, they're not very good at context. But compared to past models, they are. If I have a sentence, I give a sentence to a computer, the rabbit quickly hopped, the turtle slowly crawled, and I said, hey, count the number of words. All words are the same. They're all equal to most to computer. If I start doing a lot of traditional, language tools, all the words would be the same. And we know that's not true in English. We know if I remove the word the, you can still understand the turtle slowly crawled. Turtle slowly crawled. It may sound like a 2-year-old said it. Turtle slowly crawled still makes sense. Rabbit quickly hopped still makes. You can remove the and it works just fine. It sounds kind of dumb, but still works just fine. Now you remove rabbit, it completely changes the sentence. The blank quickly hop. Well, that doesn't make sense. The quickly hop. The quickly hop. So LLMs, one of the things that attention is all you need kind of provided us, it was the ability to focus on certain parts of a sentence, we'll say, a certain word maybe, or that certain words may, be more related to other words. Okay. So that was one of the really big advantages of let's say the last 5 years in LLMs. So let's go back here, and I just want to say, the way it works is that not just you have these simple neurons, blah blah blah, and it's in and out. When we say, hey, this model has 1.5 billion parameters, we're talking 1.5 billion basically interconnections. 70 billion parameters. When you go to Hugging Face and you see that 70B, 300B, I think DeepSeek R1 has 681 billion connections. So, I mean, that's a ton of connections. That's a lot of connections. Okay. And our brain has even more. Okay. So it's not just, I don't want you to think that, hey, it's a very simplified model. Hey, we're taking all the words and, the rabbit. No, no, no. We have millions of these things interconnected all together to kind of to understand, hey, when you put this in here, it goes to this weird matrix and we get this output. So it is much more complex than just a simple neuron. Now, it's always hard to try to show the impact of this. And there's actually 2 new drugs, but this one, there's a new class of antibiotics. Again, remember I work in healthcare, but just think about this. This is just, to me, mind-blowing. And this is not even the best example I have. This is just one of the things I thought of. But a new class of antibiotics discovered by AI. So not a new antibiotic drug, a new class of antibiotics. So multiple antibiotics. A deep learning algorithm, so a neural network, helped identify new compounds that are effective against, I think MRSA is what they were effective against. Antibiotic resistance is among the biggest global threats to humanity. It's responsible for an estimated, let's say, 1 million deaths a year. So we just had an AI that helped us save approximately 1 million deaths a year if it gets through, FDA approval, and $50 billion in sales a year. And I mean, with patents, everything, I mean, you're going to be able to lock up those sales for 20 years. That's a lot. That's a big impact. AI did this. And this is just one of 100 examples I have of how AI and this, I mean, look, what's this, 2023. So ChatGPT was out, but not really super popular. It was 2 years old. I mean, they were using traditional deep learning. So they're not using all the cool tools that we have. And still, AI discovered a whole new class of antibiotics. And it was like, I think the last antibiotic before this was 50 years, 40 years, the newest class of antibiotics. Major breakthrough. And again, the way that this happened, the story behind this is it was humans and basically AI working together. It wasn't one or the other. It was a synergy of the two. Which is, I think the big point of this is, hey, the machine said, hey, try these things. The humans did it, played around, and gave back. So it was a teamwork. It was a synergy. So now we covered the big data, the last book, the BDF book, the big data fundamentals. And you're like, hey, that's all boring data. And it is. And data is the foundation of learning, of LLMs, okay? So one thing that happened is we went from an analog age to a digital age. And what do I mean by that? So if I, let's say that I like typewritered a piece of paper and didn't have a copier, and I had to make a copy of that page I typed. How would I do it? I'd have to type it again. It was horrible. Um, and so that is an analog age. If I had a VHS tape and I had to make a copy of it, I'd have to have another VCR and, like, I don't know, click it up somehow and put one tape in, hit play, hit another VCR, hit record, and then just watch the whole show for an hour or 2 hours or 3 hours, you know? If it's a Snyder video, you know, that Justin Snyder video, the 3 hour video, it's 3 hours. I'd have to watch it on a VHS tape. Well, recently we moved to a digital age, and I don't know if it's 2002, 2010, 1990. It doesn't really matter. But basically, what happened is we had this error where we have ones and zeros and everything's digital, and we can copy things very quickly. I can copy this PowerPoint in a matter of seconds. You know, I don't have to print it out, take it to a Xerox copier and copy. I just copy and paste. This digital age has completely changed the way that we deal with information. And now we're creating more and more information. The amount of information we're creating every day is just mind blowing. We cannot fathom the amount of information created every day, just in sensors and people typing and videos and everything else. And on to that point, traditional LLMs were mostly looking at text, not web campus, like Wikipedia and encyclopedias. Now more modern LLMs go through YouTubes and look at the spoken word. They look at movies. They look at every piece of information they can get, every piece of digital information they can get to try to get smarter. When you're really young, maybe your parents just read you books. You know, the big bad wolf, you know, Snow White, blah, blah, they read to you. As you got older and more advanced, maybe you read to yourself. Then as you got a little bit more advanced, maybe you watch educational videos. This is the progression we're seeing in LLMs. Traditional LLMs, like some of the things maybe I designed, just mostly use text. I have a few projects where we're taking YouTube videos and we're using those for LLMs. And so, you know, you have this growing big data explosion. So that's why this is kind of important. I know I covered it before, but it is really important. Like I said, just a raw amount of data that we are making as a society is just mind blowing. Now, it's hard because this book doesn't really it covers a bunch of words in a bunch of different areas. And for me, it's sometimes hard because I'm reading it, you know, I read a book, I'm like, oh, this word's not, oh, what this word, and so I want to cover some terms. So, the bulk of the next like 2 or 3 slides is just terms. Let's just talk about some words so we know what they are. Okay, we talk about artificial intelligence. This is this corpus thing. It could be this huge, you know, it could be linear regression. Hey, I'm gonna do my my machine learning, my artificial intelligence homework tonight. You know, blah. Or hey, I'm gonna design an LLM that solves cancer. Or I'm gonna, you know, it can be this big, encapsulating, massive thing. So it's kind of a buzzword. So this book uses the word natural language AI, which is not a really common term. Most people say, you know, NLP or hey, NLP scientist or AI and NLP, natural language processing. And it's just going to take, we're trying to understand language as humans do. I guess that's one way to think about it. Bag of words is an older, but not bad. Okay, just an older way where text is converted into a collection of words, ignoring grammar, word order, typically occurring frequency count. So if I was to take this book and convert it to bag of words, you'd expect a, the, you know, I don't know, in, this. Those would all be very popular in this book. It doesn't really tell me anything about the context of this book. Less frequent words would be, I don't know, query routing, agentic rag, you know, a Lego block. I mean, I bet Lego block only appears in this book like 3 or 4 times, where this appears probably 1,000 times. So bag words just basically take it all and you break the words up into individual words. And, you know, we talked about this before in terms of tokenization, just really general. This is an older method, but it can still be important, you know. Tokenization is the idea that we take the sentence and kind of break it into units or conceptual ideas. So maybe I don't want to get a ton into it. We're going to go into it here in a little bit, but we're breaking the words into subwords. So instead of running, it might be run. We might stem. We might get the root word. We might lemonize it. We might correct spelling. We somehow take a sentence and break it down into kind of what it means. Not necessarily what it means, but the cat is running. I might not need the. I might be able to get rid of that. Cat is running. And cat is. That maybe that's one token. It's not, but it could be. And then running. So you break it down into a more logical way for the machine to handle it. Tokenization is the way we take our language and kind of convert it so a machine can understand it. Okay. I guess that's a really good example of it. We have a spreadsheet. We have a lot of data, and somehow we have to import it into Excel. That's the method of tokenization. We have rows and tables. Tokenization is very similar. We take our sentences, our words, and we kind of convert it so an LLM can understand it. Corpus is just like a collection of something, a collection of text, a collection of books, a collection of code. So, when you're working on LLM, you need to fine tune it. You might have, for a lawyer, you might have a corpus of legal documents you want to train it on. This book has a word vocabulary. You know what vocabulary is? Okay. Vectors. They call them dense vector embeddings, but we need to really think about what a vector is. And I don't know, the way I always learn vectors, I always think of vectors. You can't just have a car going 55 miles per hour. If you guys took some physics classes, a vector has to include direction and all these other things. A car is going 55 miles per hour relative to, let's say, the, I don't know, highway northeast. Vector has direction. Okay. Well, when we convert words or sentences into vectors, they have that same direction. So bag of words, I just say, hey, the word A is 1, the is 2, I don't know, this is 3, and then I just count them all up. It doesn't really tell me, it doesn't have that context. Vectors have context. Okay, it understands that the word dentist, like dentist. Matter of fact, guys, I have surgery later this week. I won't be around on, I don't know, Thursday and Friday, but the word dentist, D-E-N-T-I-S-T, is different than dentist, D-E-N-N-I-S. But if you mumble or you're on a phone and people can't hear you, the transcription service might miss those two words. And a non-logical sentence would be, I'm going to go to dentist to clean my teeth. The logical sentence is, I'm going to go to the dentist to clean my teeth. Well, if you put both sentences in kind of a vector, you compare them, you're like, oh, hey, there's only a few characters, not even a few words, just a few characters that are different. So these two vectors, these two directions, these two semantic thoughts are very similar. They're different, but they're very similar. I'm going to go to dentist, D-E-N-S, to clean my teeth is considerably different than the idea of, hey, look, there's my kitty cat. I mean, they're very, very different ideas. So a vector has that dimension, that shape, that momentum. Okay, we'll go into vectors more. There's a couple different types of models we'll deal with. Encoders and decoders. We're hit BERT topic. It's a very easy, very good model for beginners to start learning with. It's an encoder only model. Don't worry about a ton of that. And we'll use GPT, which is generally a decoder only model. Okay. Yeah, I guess that's I have a couple slides on it, and I have I think a Medium article that goes into a little bit more. Word2Vec is a algorithm that basically uses, I guess, a neural network to generate word embeddings by learning word relationships from a large database. So that dentist and dentist, I discovered that through Word2Vec. So it just basically takes a word and kind of makes it a vector. Okay. So now quantization, I did not teach this in my last classes, and it's becoming more and more important. So quantization is the idea that we can take a model, one of these big 70 billion model or a 700 billion parameter model, and we can kind of compress it. We can kind of shave off, everything that we need. And I don't really like the word compress, but we can kind of trim it and make it fit in a more practical, smaller machine. It's kind of weird. But so I have I have a car and it has 8 cylinders. But am I really using all 8 cylinders when I drive? Am I like getting the gas all the time? Am I using, am I at 6,000 RPM? No. My other car is a 4 cylinder, like a small, like 1.6 liter 4 cylinder Toyota. Um, and you know what? When I drive to UNLV, both the V8 and the 4 cylinder work just literally just as effectively. The 4 cylinder gets better gas mileage, i.e., less energy. Big models, the 700 billion parameter models require more energy, i.e., worse for the environment, more carbon, blah, blah, blah. But so if I can find a way to trim these models and achieve the same thing, then that's really important. And there's different ways to do it. But basically, one of the ways we're doing is we're not using everything the model knows. We're only kind of trimming or using the most, not really the case, we're using the strongest pathways. From here to UNLV, a 4 cylinder, 8 cylinder is not that much of a difference for me. I don't go 100 miles down, 100 miles per hour down Flamingo. There's no real functional difference between my 4 cylinder and 8 cylinder when I drive from here to UNLV. Except for one, my truck gets 10 miles a gallon. My Corolla gets, I don't know, 30 to 40 miles a gallon. So Hugging Face is a place where you can have open models. You can get quantization, you can get quantized models, you can get full-size models. It's a place, it's a newer website where you can get models and share, and it's a community site. Like, I guess kind of like Reddit, but it has models, like Instagram, but it has machine learning models and pipelines and data and things like this. Attention mechanism, we kind of talked about that, but basically the attention mechanism is simply where we are trying to figure out what is important in a sentence, what is important in a paragraph, what's important in a class. Not everything that every teacher, any class that you take, some things in a class are more important than others. How do you know that? Well, as you become a better student, you can ascertain what the teacher wants and what's more important. Well, how do we do this with a machine? Attention mechanisms. Attention is all I need. Self-attention, things like this. Okay, so next slide. Okay, so like I said, this is kind of a hodgepodge of different lectures I provide. And this one, I normally give this earlier, but when we're looking at text, it's something important to remember. What are we looking at? Are we looking at the text? Am I looking at the book? Okay, so if I look here at the physical book, I'm looking at the words, okay? Or am I looking at the metadata that says, hey, made in 2024 by blah, blah, blah. So the metadata tells me about the text. When was it published? When was it written? Maybe how many words? So if I'm looking for reviews for the iPhone, okay, so the context is all the reviews for the iPhone. I start putting that down, blah, blah, and I'm like, hey, what's this person talking about? They get no 3G signal. Oh, because my metadata, I need to specify the metadata. I only want reviews, let's say in the last 4 years. Let's say 5 years, from 2020 forward. I only want all the reviews on the iPhone for the last 5 years. So I use a metadata to kind of shape, filter my context. And then scores are just something that we kind of do after that. So we have a text. We can talk about the readability. We can talk about the sentiments, positive, negative, things like this. But this is kind of important to understand. Now, this is also with pictures. When I take a picture on my iPhone, I have all the metadata. Let's see here if I can find one really quick. Okay, so okay, so here, this picture, it's a picture of my 3D printer. I shot at, okay, I can't read it, yesterday at 6:30 a.m. Okay, here is, I shot it with, there's all the settings. So the metadata is I use the main camera at 24 millimeters at f1.76, use a rich contrast filter. The metadata says it's an HEIF, and again, we're not saying anything about the picture. 24 megapixels, 4284 by 517 is 2.1 megs. It's nothing to do with the picture. You know, I mean, you can trust me, there's a picture of my 3D printer, like my filaments, but it's about that picture. Same thing as metadata. You know, it's about the data of the conversation. And I know what you're saying. Oh, it's no. Metadata is vitally important as context. There's information storage or other information about how the NSA uses metadata more importantly than actual call transcripts. Now, what do you mean? So if two people, let's say two terrorists, go into a coffee shop and they turn off their phone at the same time, yeah, maybe once that might happen. But if it happens 2 or 3 times, they go to different locations. Or you have a person, and anytime he goes into a location, he turns off his phone, and so does somebody else. And then he goes to another location, the other person turns off their phone. You know somehow they're related. You don't know what they're talking about, but that metadata is vitally important. We know we can predict people's patterns in the future just solely based on metadata. So metadata is super important. So what do we have here? So this is kind of going more to kind of chapter 2-ish, but I just kind of wanted to talk to you about it. So general concepts in NLP, and some of these are hit and miss because sometimes you want to do this, sometimes you don't. But a lot of times when you get text, you want to remove special tags or characters. You know, if I'm sending it to a traditional NLP pipeline, we'll say, maybe I want to remove any weird non-American characters or, you know, the tilde or things like that. Maybe I don't. Maybe I want to break my words into individual, maybe sentences into individual words. I want to tokenize it. There's different methods to do this. Maybe I don't. Normalization. Maybe you want to remove all the running, ran, blah, blah, and make it all the same. Maybe you want to do some basic, I think I go spell check on the next one. I don't know. Oh, but so there's certain types of normalization that can be done on data. And again, all this stuff's not hard. You just run it through Python pipeline, blah, blah, blah. I actually know how to do that, but don't worry about this. It's more important to understand the concepts. Now, so stemming and liminalization. So these are two of the important ones, and I think they're kind of dying down slowly. We still use them a lot. I mean, I use them every week, but I think more traditional machine learning models now are trained on unstemmed and unliminalization words. But the idea is stemming, you basically reduce the words to the root form by removing prefixes and suffix. Okay, so running become run. No, I guess that makes sense. Fishing becomes fish. Okay, liminalization now converts it to the base form of its dictionary. I get this backward. And liminalization is where you go from running to ran, or you change it to the actual core fundamental idea. I always get stemming and liminalization mixed up. So if I get those mixed up, it doesn't matter. But it's important because when we're trying to understand words, future tense, past tense, and present tense can throw machines off, can throw humans off. My wife makes fun of me because I don't generally write, I don't always add ing to my words. I just write, and even when I talk about the future, I write in present, or the word data. There's weird words. So stemming and liminalization help clear this up. You can also do lowercase. Sometimes you want to lowercase everything, even names. Or you want to do stop word removal. Stop words are words that may not add context to the sentence. As an example earlier I gave, I talked about the rabbit quickly jumped. The word rabbit doesn't, the word the doesn't really add a lot to that sentence. The sentence functions just fine without the, and spelling correction, blah, blah. So, there's different ways to kind of clean this up. So let's go into stop words. So stop words can significantly reduce the size of a data set, which in turn decreases computational load. Like I said in the book, in this book or any book, the number of A's, thes, this step, a retanker, after, a lot of these words don't add value. The sentence still makes sense. It may not be grammatically correct, but the sentence still makes sense if you remove the thes, the A's, the ends, things like that. And it makes the pipeline process faster. I mean, dude, you take out all the A's, is, thes, ands, is, ors out of this book, it's half the size. It really is. It's half the size. And so we can run it through smaller computers. We can run it faster, and we'll still understand it. Hopefully, nowadays it's not necessarily as big as issue. I don't think as many, models are per se trained on things that have stop word removed. Some are, some aren't, but it's not as common as it was, I don't know, 3 years ago. We still do a lot of stop word removal. If I have to pay to send something off to OpenAI, and I'm sending a million phone calls, removing stop words saves me, $20,000, $30,000. So, yeah. So here's me talking a little bit about why it's not always necessary. I have some code I'll share with you. Hey, here's a sentence before stop words, and here's what it is after stop words. So you can kind of see right here. I think these are real estate. It looks like real estate. Under construction, estimated completion NA. So just remove the word N. Under construction, estimated completion August. Absolute darling one-story home in charming. Absolute darling one-story home charming. So you can still read it. So okay, so now let's kind of go to specific parts of the book. Okay, so your book has a really, I do love this figure 1.2 in the book. We can throw multiple things at ChatGPT. We can throw multiple things at LLMs. Okay, and they're not specifically talking about LLMs. They use the generic word language AI, but with a NLP or with machine learning in relation to NLP, we can do a lot of cool things. We do text output. Okay, so what's the capital of Nevada? What's the capital of Utah? We can do these things. We can start doing predictions. Hey, can you help me reword this sentence? Can you help me finish this sentence? We can do summary. I can send an article to ChatGPT or to a lot of things. Hey, can you summarize it? It can do classification. And some of the more advanced models can now do multimodal things. Hey, can you make a picture from this text? So again, these language models, we give them unstructured, rough text, misspelled, uncapitalized, and they come out with semi-beautiful text, semi-beautiful results, which is fundamentally amazing. So let's go to the transformer model. So like I said, if you want, I don't even know, I think maybe one extra credits, I might even have you all look at the 2017 paper, Attention is All We Need. But the big picture takeaway from the transformer architecture, and I know this book goes a little more in detail, is we replace recurrence on RNN looking over something with self-attention. So instead of using a recurrent neural network, the transformer relies on self-attention to capture long-range dependencies. So long-range dependency, I have a text, and maybe something at the top might be related to the bottom. Okay, so where's that long-range dependency? With recursion, it's a very different method to try to capture that. If you look at LTSM networks and other things, it becomes more difficult to understand the past. Now, what do you mean? If I said, hey, I want to look at Ford, since I know one of the CEOs, not like I know him, but I want to look at Ford stock prices. Okay, so I look from when Henry Ford, see, that's CEO, wherever he was, when Henry Ford was running it to today. That's completely stupid. Because his actions back 100, 150 years ago may not directly contribute to tomorrow's stock price of Ford. Today's CEO will, and maybe even the last CEO will. But where do you draw the line? Hey, I only want the last two CEOs and see how their performance affects the stock prices. I don't think Henry Ford and his son and all the other Fords that ran Ford Motor Company have a direct impact. I'm just saying Ford is the only one I know. Have a direct impact on the price. So that's self-attention. Is how does a machine, how do we focus self-attention? How do we replace recursion with self-attention? So that's one of the things that attention is all we need to come into that parallelization. Instead of having, one pipeline, now we can have multiple stacks, multiple pipelines. And your book also goes into Mamba and RWKV. Mamba I know a little bit more about, but RWKB, matter of fact, even reading the book was the first time I really heard about this. Maybe it's something else I'm just not thinking of, but so there's a lot of new types of architecture. Okay, but the idea of really, when we hear transformer, and again, transformers or attention mechanisms is not just in large language models. We use it in stocks. We use it in a lot of other things. But what made it so dynamic is self-attention. How many CEOs do we want to focus on to predict stock prices? 10 is too many because they're dead and they're in 1960s and 70s. Maybe two or three is important. Parallelization, instead of just me trying to figure out the best price of forward stock, maybe have my whole class do it. Okay, so that's kind of where the transformer gets strength. Your book does talk about BERT a little bit. One of the key issues, and I think the book maybe loses focus a little bit. One of the really cool things, one of the ways that BERT was trained is by masked words. And as a human, you can think about this. If I provide you a sentence and white out one word, cross out one word, you should be able to figure out, just from your experience, what that word is. How are blank doing today? How is dog doing today? No, that doesn't sound right. How is iPhone doing today? No. Come on, guys. What's the word we're looking for? How are you doing today? Now, I'm sure there's a sentence on the internet I probably could find right now in Google. How are dog doing today? I'm sure I could find that. But the probability of that versus how are you doing today is much less. So we're just looking at probabilities. What is the most likely, the most word that will go in there? No different than the way the humans do it. When I say, how are blank doing today? Your mind automatically goes and figures out what word should be in there. I mean, you can come up with 100 words that would fit in there just fine. But deterministically, probability, that how are you doing today is the best fit for most scenarios. Here's a little bit, I found this, I think I included the article in the web campus about the difference kind of between BERT and a GPT model, between your encoders and decoder only. I can leave this up. I don't, just to understand the major 10,000 foot overview of what the difference is. GPT kind of predicts the next word, tries to predict the next word. BERT, your encoders try to predict mass words. Now, not that they can't do the same thing, just maybe some are better at some things and some things are better at other things. Okay. So I'll leave that up there for one more second. So now, your book does a really nice thing about the two-step training. So the pre-training, and it's kind of weird the way they kind of break this down. So we'll say the pre-training is a big data fundamentals book. The one that has a cool picture, the black and white, the PDF book. We'll say that is a pre-training. We get all the text, we kind of clean it. That's why I had to teach you Lord Corpora. We get the corpus of data. We get all the legal documents we need to make a legal LLM. We get rid of all the page numbers on the side. Maybe we get rid of all the dates. We get this beautiful set of data, and we start handing it to a model, and then the model starts going over and over and over again. We start training it. Okay. Whatever the corpus that we have this big set of data, and we make a model. That's right here. Then what we do is we take this model and we want to fine tune it. We want to optimize it. A lot of what I do is take these base models and fine tune them for disease prediction. How do I do that? Well, I look at certain diseases, neurodegenerative diseases of the mind, not of the actual body, like heart disease, end stage kidney failure, things like this. I try to remove that. I try to take an LLM and I work on neurodegenerative diseases. And I take those neurodegenerative diseases, a bunch of PubMed papers, a bunch of scholarly API papers, anything I can find. And I say, hey, now let's update what you know and let's fine tune it. So this is kind of how we do the fine tuning. We get a bunch of data. We get all the encyclopedias. We get all the YouTube videos. We get everything we can. And it says unsupervised. I guess that's more or less true. And we create these LLMs. Then from that LLM, we fine tune it. And so this is how we get optimal models. So I'm not a big supporter of, hey, here's a midterm, write me blah blah blah. Last year for this class, basically my midterm it was horrible. Well, not horrible, I shouldn't say that, but it was a 3 hour. It was broken down into two videos, but it was a 1.5 hour times two video on ethics and AI and responsible use, and that was my midterm. You just had to watch it, dude. You just turn on your phone, watch a video, and I look and make sure the students watch it, and boom, that was your midterm. I might do the same thing this year, maybe make it a little bit less. Just watch it over spring break. Nobody cares. Watch it while you watch TV. I don't care. I hope you actually watch it and pay attention because these are really, really important fundamental things that will affect everyone's future. But when we design AIs and when we make LLMs, we have a lot of ethical considerations. I go and watch talks from Berkeley, and they talk about the racial bias in the text in AI. What about the training? There's a book, Weapons of Math Destruction, that talks a lot about bias and fairness training, just in general standardized testing, like transparency and accountability. A lot of times we don't understand what's under the engine. If an AI makes a prediction, we might not understand how or why it made that prediction. What about misinformation, intellectual property concerns? If I put in social security numbers in an LLM, is it trained on that? What about regulation? There is a lot that we don't know in terms of AI, in terms of ethics, regulation, and long-term impacts on society. And it helps to think about it. So maybe this year, maybe like I said, for the midterm, maybe I'll do an ethics lecture. I welcome your feedback. It's better than doing anything real, like having to write something down or multiple choice. I think we have just this last topic, we have open source versus closed source. So there's different ways to connect to a large language model. Your book kind of talked about this, but it is super important because I think most of us feel that when we connect to, I don't even know if I have it open here, if I can get it, but when most of us connect to ChatGPT or Claude, we just go to a website, OpenAI, blah, blah, and type in our query. That's a web interface. Probably how 90% of people do it. I don't know, 95% of people. They go to deepseek.com, type in their question, boom, move on. Or mobile app. Hey, well, I can't say anything because Siri will start talking. But hey, blah, blah, blah. Can you answer me this question? So those are two of the very common ways, mobile app and web interface. But that's not how a lot of the power users, I hate that word. That's not how a lot of people actually do it. A lot of times we use API, application programming interface. So basically what we do is we find a programmatic method to send text to OpenAI, to Claude. It's command line tools. So now why do we do that? If I'm looking at, I mentioned, hey, if I'm looking at the iPhone reviews, I have 1 million iPhone reviews. That is too large for me to put into a single prompt. That's too large for me to put in a single question. So I have to figure out a way to mathematically break up those questions, those reviews, and then programmatically ask ChatGPT, hey, how do you do this? We'll be doing, I think we do some API. I have an API here at my house for an LLM, and I'm trying to think if I want to give you access how I want to move forward with that. The DeepSeek tutorial I posted, that the Grotto hits basically kind of like an API, local API, to ask it questions. So I made a web interface, and you can see the way the web interface hits the model in the background. So this is how we connect to LLMs. Your book covers it, and it is super important because, as a beginner, we hit web interface. But as you become more advanced and we learn more, we use APIs because we can do more, we can send more, we can specify things better, we can become more accurate. Now, something that is becoming more and more important, and I did not cover this last year because I didn't think it was going to be an issue, is open source versus closed source. So open source versus closed source in terms of software has been going on for, I don't know, 30, 40, 50 years. And the idea is, do I share my code? Do I share my code? And there's pros and cons to everything. Windows is a closed source operating system. Red Hat or Linux is an open source operating system. Some things to think about. And there's two kind of things. The iron triangle, which I'll cover a little bit later in the semester. Things can be cheap, fast, or good. Pick two. And with open source, there's nothing more true than probably that. Here's a little bit more extended version of that. When we talk about open source and closed source, you need to think about security. You need to think about cost. You need to think about customization and flexibility. Now, what do I mean? So, security. With Windows, I have to assume, and you know what happens when we assume? I have to assume that Windows is looking after my best interest and protecting my Windows machine, or my Mac. I have to assume Apple is looking after my best interest and securing the operating system. With Linux, or with BSD, I can actually go in line by line and look at how they do things. And if I find something wrong, I can raise an alert. Say, hey, this is wrong. This is a better way to do it. And that's a huge factor right there. With cost, I have to pay for Windows. With Apple, you pay for it when you buy the hardware. Linux, you can just download for free anytime. Well, it's just one person, not a big deal, Richard. What if you have 1,000 employees? What if you have 50 employees? OpenAI Pro costs $200. If you have 10 employees, that adds up really quick. DeepSeek, DeepSeek R1 is $0. 100 employees, this is a big cost difference right there. DeepSeek R1 free, OpenAI Pro, $200. 100 employees, 1,000 employees, it adds up really, really quickly. But what's the cost benefit? What's more customizable? What's the solution? So here, and not that one's better than the other, because that's not what I'm trying to get at. Because I use both all the time. Every day I use both. And I have a little picture of that. But so let's just talk about a few open source ones. And there's tons of them. DeepSeek, just because it's been in the news a lot. Llama from Meta, from Facebook. These are all open source ones. You can download, put on your computer, unplug your computer, and play with them all day. Nobody cares. It's up to you. That's that's what an open source model is. I can take DeepSeek and tune it. I have a DeepSeek one that's specifically designed for coding. These are all things I can do with open source models. They're fully transparent. They're customizable. There's no vendor lock-in. There's also no support. If something breaks, guess what? Too bad. You also have to have hardware. We're talking about 5090 now, and it's like $2,000. That's not even enough to run most of these models in a fully powerful form. You're talking cards that are $80,000. $80,000 for a video card, for a GPU, and you get 2 or 3 of them. Even a relatively weird card at $25,000. Yeah, you can buy a car for that. So sometimes you require powerful hardware and expertise to install it. With ChatGPT on my right side, a 2-year-old can go to openai.com or chatgpt.com. Hey, what is a bib? Or what is this? And a 2-year-old can literally operate ChatGPT. They're much easier. But then again, you have to pay for them. And you're always paying for things like that. You might not be paying $20 a month, but they get to use your data to train it. Just like Gmail, you may not be paying for Gmail, but they're using your information to send you ads. You're paying for it in one way or another. So don't think because a closed source system is free, you're not paying for it. You're paying for it one way or another. You're releasing your data. You're losing privacy. You're paying for it just in different ways than monetary recompense. Now, these models are generally optimized. They're high performance models. Any day of the week, Windows and Macintosh look better, run better, and generally, I don't want to say more stable, but they look prettier than Red Hat, than Linux, than Ubuntu, than Mint. Okay? It's just the way they are, but you have to pay for them. So, let me keep going. So there's a site called Llama. This is a page where we can download models. I just went to it yesterday. You see, hey, I can download DeepSeek, all these different models. It has 7 million polls. 7 million people download it. I can get an 8 billion parameter token. I can get a 70 billion parameter model. I can get Llama from Meta, from Facebook. 70 billion parameters. I can get Phi. I can get Llama 3. I can just go and download this just as you can in Hugging Face. You can run them. They're open source. I can see the code behind them. I can download. I can do everything. I don't want to say they're mine, but they're mine. And some of them have restrictions. I think Llama, like if you make more than $1 million a month, you have to do this. But for the most part, you can download them on your computer. They're yours to play with. Nobody has to. You can unplug your internet. They're your source. But then again, you have to have the compute to run it. You have to know how to install software. You have to know what to do with the model. It's not just like, hey, double click and run. Now, one of the sites I use a lot is OpenRouter, and OpenRouter is just an aggregation of different models. And so this is well, this is my OpenRouter account, but it doesn't show that. But if we look, so this is LLM ranking. So this is from OpenRouter. This is from yesterday. I don't know, February 2nd, 3rd, 4th, something else like that. So let's look at what we have. So currently, the number one model is a closed source model. Number two is closed source, but they're pretty much the same. So I think Google, I think these two, so 1, 2, 3, and 4, I think those are all closed. Actually, I think number 4 might be an open source model. I'm not 100%. I just don't know in Mistral. I thought it was down open source, but I read somewhere that it was closed source. So I don't know. So 1 and 2, anthropomorphic and Google will say those are closed source. Mistral will say it's open source. DeepSeek will say it's open source. Llama will say it's open source. And we'll say ChatGPT is closed source. So we have a mix between open source and closed source models. So it's not like you just use one thing or the other thing. On my Mac and on my Windows, closed source, I use Python, open source. I use Pandas, open source. Okay, so it's not just one versus the other. Okay. Now, just real quick before we leave, this is my last slide. I have to check. I might have one more after this, but when we use large language models, and we're seeing this with DeepSeek, there's always privacy risks. So don't put anything in there that you might not want out in the public. With OpenAI, even if you pay $20 a month, they can use your prompts for training. You have to pay more to not train on it. There might be algorithmic bias. Dude, it's trained on the internet. The internet is not the most fair and peaceful place in the world. There's algorithmic bias. I'm not going to lie, that there is. And not only that, once we start deploying AIs, we see downstream bias. If an AI says, hey, there's going to be more crime in 89123, so we send more cops. Guess what? More cops inherently cause more crime. Not cause more crime, they detect more crime because they're there to detect it. Just recently, I guess a bunch of FBI agents here in Vegas either got laid off or asked to leave, a bunch of stuff. I really don't have it. So let's say you get rid of like half the FBI agents here in Vegas. How's that going to affect crime? It's not. Crime is going to be crime. Now, the solving rate and the closing case rate, those will all be affected. But you can fire every FBI agent and crime's not going to go up or down. Now, how we solve those crimes, the conviction rate, all those things will be affected, but not crime. If we send a bunch of cops to one area, the crime doesn't really go up or down. We just detect it more. We also have misuse and abuse. We can see a lot of AI is being misused to do bad things. And transparency and accountability. If an AI tells you how to do this, well, is it right or wrong? That is why it is so important that I ask you all the time, say, hey, just cite OpenAI or cite, hey, I use ChatGPT. I don't care. I use, a Copilot. I don't care. I just want you to cite it, So again, guys, I'm looking for your feedback. I'm looking for questions. I'm looking for your thoughts. This class is a graduate level class. It's not there to be didactic. It's there to make you think and question. So I welcome your feedback. Otherwise, I hope you guys have a good week. I'll get the next lecture out a little bit later today. It is just a real light review of tokenization because I kind of want you to focus on your research project. Otherwise, have a great day and hope you're doing well.